Okay, so thanks. So this is going to be joint work with Shiriron and Jan Vondrak. Let's start with okay. So let's start with maybe the most basic mechanism in the mechanism design, which is the second price auction. And the question that I want to ask is very simple: how would you bid in a second price auction? Now, I'll actually give you several possibilities for what I mean by a second price auction. The first one is when you and the other bidder simultaneously submit bids. That is, you both write down your bid, put it in an envelope, give it to the auctioneer, which opens the envelope simultaneously and announces the bids. Okay, and the bidder with the highest bid wins, and you pay the second bid. Okay, so as we all know, your dominant strategy is simply to bid your value. Okay, so this is very simple. Now let's consider another implementation of a second price auction. And in this implementation, you submit your bid first, then the other bidder sees your bid is publicly announced, and then the other bidder submits his own bid. Okay, so the question is, how would you bid now? And the answer that might be surprising if you haven't seen that before is that there is simply no dominant strategy for you. Why is it so? Because your competitor might use like unreasonable strategies. Like, if I bid, if you bid 10, then I'll bid 20. Otherwise, I'm always bidding 0. Okay. In that case, if your value is 10, bidding 10 is not the right thing to do because you're going to lose the item and get a profit of 0. You should bid, I don't know, 11 and get the item for free. Okay. So no dominant strategy in this implementation. So what we see here is that the details of the implementation of the specific mechanism matter to the existence of a dominant strategy. So and that's exactly what we're going to investigate in this talk. So this is like sort of like a notation slide. I want to actually, since we care about the specific implementation of software choice function, we're going to consider the extensive forms of mechanisms. In this slide, it's only going to be like the extensive form of a second price auction, but this is general. And in all mechanisms that I'm going to talk about in this talk, we're going to have private information. All mechanisms are deterministic, and we're going to use the blackboard model. In other words, everybody sees the actions of everyone else and know in which node they are in the game tree. Okay, so let's consider several implementations. Let's try to draw them as trees in the standard way. So in the serial implementation, Alice bids first, Bob bids later. Alice makes some bid, then Bob sees her bid, and he makes some other bid, and then we have the outcome. Okay, so for example, if Alice bids 9 and Bob bids 1, then Alice wins and pays 1. If the bids are 9 and then 8, then Alice wins and pays 8. Okay, so this is the serial implementation. Good. We also have the ascending auction implementation. Here, say Alice starts, she has 2 options, stay or quit. If she quits, then Bob wins, pays 0. Otherwise, it is Bob's turn. Bob can decide whether he wants to stay or quit. If he quits, then say the price increases by 1. Then Alice wins and pays 1. Otherwise, it is Alice's turn again, and so on and so forth. Okay. And we also have the simultaneous implementation in which Alice and Bob simultaneously make a bid. Okay. In which Alice and Bob simultaneously make a bid. So now the edges are labeled with the bids of both 1 and 9. That means that Alice makes a bid of 1 and Bob makes a bid of 9. 50-72, Alice makes a bid of 50 and pays 72. Okay. So questions so far? Good. Let's try to formalize this notion of when we have dominant strategies and when we don't. The relevant notion here is the notion of ex post implementability, which talks about basically about the outcome. So an allocation function f is ex post implementable if there is a payment function such that for every two valuations, VI and V prime I of player I, and valuations of the other players, player I with valuation VI prefers the outcome when the input is VI, V minus I, over any other outcome, V prime I, V minus I. Okay, so this is sort of the standard thing that we use in algorithmic mechanism design. Okay, so it tells us something about the outcome and doesn't say anything about how we have reached this outcome. Okay? We're going to contrast this notion of ex post implementability with the notion of a mechanism that has a dominant strategy equilibrium. Here, a strategy is dominant as usual. So a strategy is just like a function that, given your private input and the node that you are in the game tells you what action to do. A strategy is dominant if it is always better to play this strategy, no matter what the other players are doing. Okay. If we have some dominant strategy equilibrium, S1 to Sn, then we have like the, that naturally defines some outcome, F, some allocation function, who gets what, and then we say that A is a dominant strategy implementation of F. Okay? So, that's what we have. And we, of course, have the revelation principle, which basically says that every ex post implementable function can be implemented by a simultaneous dominant strategy mechanism. Okay, what does that mean? So if you have some ex post implementable function and you ask everyone to just simultaneously submit their valuations, their types, then the central authority can compute the outcome and we get a dominant strategy equilibrium. Simply because everybody is doing everything simultaneously, there is no way to threat anyone else. If you do that, then I'll do something that is bad for you and so on. Okay? So the revelation principle simply tells us that the notion of ex post implementability is strictly stronger in a sense than dominant strategy implementation, or not strictly, or stronger, not strictly, because we can implement every function that is ex post implementable with a dominant strategy equilibrium. Okay. Just like one word about the meaning of being an ex post implementable, it means that, roughly speaking, that truthful bidding is an equilibrium. So if everyone else is bidding truthfully, then you should bid truthfully as well. But it doesn't protect you from inconsistent strategies, just as we've seen in the serial implementation of a second price option. Huh? Questions so far? Okay. So what we want to understand in this talk is, do ex post implementation—
Inconsistent strategies, you mean non-equilibrium? Or you mean equilibrium that is not dominant? What do you mean by inconsistent strategies? You said inconsistent. What do you mean by that?
Like in the serial implementation. Like in the serial implementation, if you do that, I'll do that. Like, yeah.
You mean an equilibrium not in dominant strategies, or you mean something which is not an equilibrium?
Something that is not an equilibrium.
Ah,
okay. You're not protected from someone that is playing outside the equilibrium.
Why do you worry about those?
Like in the serial implementation, if you're not worried, then we're all good. But that might be, you might worry about people that
no,
are
I think that no, because in that example it was a different equilibrium. That was an equilibrium, what you described.
It was
in the sequential game, what you described was an equilibrium, perhaps, no? Or maybe you could make it an equilibrium.
It's an equilibrium, but it's not a very strong notion of an equilibrium.
I know, but
that's what I mean.
There is a fine distinction here. That's why I'm trying. Okay.
Okay, I agree. Okay. So what we want to understand is whether ex post implementations require less communication than dominant strategy ones. Okay, so that's basically the question that we ask in this talk. Like maybe quite surprisingly, there is a mixed evidence. So evidence goes either way. Maybe the intuitive answer is like, obviously ex post implementation is a weaker notion than dominant strategy implementation. So of course we should be able to have some function that we can implement with ex post implementation with not much communication, and dominant strategy implementation will take us much more communication. So maybe that's the first reaction. And you might also support this point of view by observing that the naive application of the revelation principle usually imply a significant blow up in the communication. You send too much information. If you have to send your full valuation, that's like many times it's like lots of information, much more than what you need in order to just compute the allocation function. But on the other hand, like if you look at mechanisms that are out there, that like ex post implementations that are out there, they are actually like dominant strategy ones. Okay, so maybe the idea is that the set of ex post implementable functions is not that big, and all of these ex post implementable functions are actually dominant strategy implementable. Okay.
But Shahar, in terms of the previous point, the revelation principle is just a proof method. It doesn't mean that you need to apply this blow up.
I'm saying like evidence in the sense of what should you think about that? Like the obvious method doesn't give you good results. It's not like proof. Okay. Okay, so like most mechanisms that we know that we call them ex post implementable are actually dominant strategy implementable. And and yes, the revelation principle is just one method. In fact, if we have like in certain environments, we have strategy mechanism in enough environments and take any dominant strategy mechanism with a very small blow up in the communication complexity. Okay, and I'll give a precise statement and actually even a proof of this statement later. Okay, so this is why maybe like there is no like a big gap between ex post implementation and dominant strategy implementations. And in fact, only recently there was like the first example in which we know that an exponentially more communication is required for dominant strategy implementation comparing to ex post implementation. But that example was for one particular like tailored environment, and not so much for the for environments that we care about. Okay? So what you want to do in this talk is to understand the relationship between ex post implementability and dominant strategy implementability in environments that are well studied, and these well studied environments are going to be like combinatorial auctions and multi-unit auctions. So let me give you a brief reminder of.
Shahar, could I ask a question for a second? Are there any dominant strategy implementations that are not simply a revelation kind of thing, or something that is like a simultaneous one-step communication?
Okay, posted prices auctions are not. For example, like right, when you price every item, and you take the first one, then you take whatever you wanted at a given price, and the second guy comes and takes whatever he wants at a given price. So that's not
sequential posted price is dominant strategy.
Are not, for example, and actually you can do like kind of crazy thing. I'll actually, if I have time, I'll show you some later, like things that you wouldn't guess that they are dominant strategy, but they are. So yeah. So no, but it's true. Okay, but it's true that simultaneous algorithms are maybe the typical kind of algorithms that are dominant strategy, and we'll see like indeed like formal connections between them and dominant strategy mechanisms. Okay?
So Shahar, just to clarify, the designer has access to the parameters of the problem. For example, in a Bayesian setup, you would know the distribution or something like that, and you have to communicate, and you only look at communication between the participants and the designer, correct?
Almost. I mean, except that I don't want to think about Bayesian settings here at all.
Sorry?
I'm not thinking about Bayesian settings here at all. There is no.
Well, if you don't think about Bayesian, what's this posted price? Then the example of posted price, what's the, I mean, so what? The mechanism says price is 10. I don't care why. Just that's because that's what I dreamt last night. And now take it or leave it. I mean, that's not a very useful mechanism unless it's tailored to some environment.
Okay, not quite. First, yes, it's not in a deterministic setting. It's not a useful mechanism. I agree. If you allow randomization, not necessarily a distribution over the valuations, but rather you let the mechanism flip some random coins, then you can actually get like.
Okay, but if we are not in a Bayesian environment, then this example really doesn't answer Noam, because in a deterministic environment, that mechanism can never be a good mechanism. Okay.
Okay, Noam asked whether there are non-simultaneous mechanisms. The answer is yes, there are some non-simultaneous dominant strategy mechanisms. And okay, like I'm almost tempted to like give you the example of that I postponed to later to show you that you can do like other things. You know.
Okay, I'll wait. Just
okay. Okay, so we have in a combinatorial option, we have a set M of M heterogeneous items and N bidders. Each bidder I has some valuation function that gives some value for each possible subset of the items. Multi-unit auctions are the same thing, except that all items are identical. So a valuation function just gives a value for each possible number of items. And the goal in this talk is going to be to find a location of the items that maximizes the welfare, at least approximately. Okay? So these are all the standard definitions. Okay, so let's see what we know about welfare maximization with ex-post implementations. In a combinatorial auctions, we know that basically we have the class of gross substitutes valuations in which communication that is polynomial in N and M is needed to compute the optimal welfare. Okay, if we can compute the optimal welfare, we can also easily compute the VCG prices and have an ex-post implementation of the welfare maximizing mechanism. So the gross substitutes, gross substitutes valuations, the definitions are not really important for now. Gross substitute valuations are easy as far as we're concerned. Everything else, the modular or XOS additive, requires exponential communication even to compute the optimal solution. So, so that's going to be hard for us, even for ex-post implementation. The situations for multi-unit auctions is actually quite similar, except that the classes of gross substitutes and some modular valuations coincide, and they're called decreasing marginal values. So the marginal value of every item decreases with the number of items.
Sorry, Shahar, sorry. I'm slowly, yeah. Yes. Why do we care about the computation? I thought you are looking only communication. I mean, the computation of the optimum by the designer, that's free, no?
Yeah.
Or I'm missing something here.
No, that's exactly true.
So I don't care that takes exponentially long.
You don't? No. Okay, to compute. Okay, maybe to compute means to communicate. You need to communicate exponentially many bits. Yeah, that was both statements are about communication, not about computation. Okay, I should have written that more clearly. You need to exchange exponentially many bits in order to compute, in order to know what the optimal solution is. Okay, that's exactly what you said.
Okay, so that's not okay. So that's the communication needed exponential.
Yeah.
That's what you mean.
The communication needed exponential. Yeah.
Okay.
Yeah. The statement here wasn't precise. We weren't precise. Yeah, but I mean exactly what you mean. Okay. So for multi-unit auctions, the situation is similar. This decreasing marginal values class is easy. Here it means that we need polynomial in N and log M bits to communicate. Okay, we need to exchange a polynomial number in N and logarithmic in M. And everything else, XOS, additive or general, needs, again, we need an exponential blow up in the communication complexity. So we need polynomial in N and M communication in order to know what the optimal solution is. Okay, so we have the same blow up in the communication complexity, but with slightly different parameters. Okay. So now we can finally tell you what our result. I'll start with a result that is not really in this paper, but is actually quite related. I'll show you that in rich enough domain, and I'll explain what rich enough domains later. Every two-player dominant strategy mechanism, in rich enough domains, two-player dominant strategy mechanisms and ex-post mechanisms needs almost the same communication, and this is going to be some like algorithmic way to convert an ex-post implementation into a dominant strategy one without blowing too much the communication complexity. Then we are going to discuss the green areas that we've seen before. We're going to show that the communication complexity of every dominant strategy for combinatorial auctions with GS valuation that outputs the optimal welfare is exponential in them. Again, we call that the ex-post implementation is polynomial in them. Okay. And the second theorem that I'm going to show you is that the communication complexity of every dominant strategy mechanism for multi-unit auctions with decreasing marginal values is omega of n. Okay. Again, before that, we needed like a logarithmically many bits in order to compute. With an ex-post implementation. Now with dominant strategy implementation, we show that we need exponentially many bits. Okay, the communication blow-up is exponential. Okay, in other words, if that was the picture before, like the green area, now with dominant strategy implementations, this becomes like an orange. This is something hard. We know that we cannot maximize the welfare unless we use like many bits. And for everything outside this area, XRS, additive, and general valuation, this is going to be like a rich enough domain in which we know that we cannot hope to have such a gap between the communication complexity of ex-post mechanisms and of dominant strategy mechanisms. Okay. Questions? Good. We also complement
Shahar, a historical question suggestion. So in Vickrey's original paper, he defined dominant strategy implementation, and his main example was multi-unit auctions with decreasing marginal values. Somehow it seems that these two things don't work together now, according to what you're saying.
Okay, so you told me that at some point that Vickrey used like decreasing marginal values. When I read like Vickrey's paper, I see that he talks about like unit demand multi-unit auction. So that's not exactly the same thing, I guess. Unless I'm misunderstanding something in that paper.
Maybe I see. Could be.
Okay. Okay, so we complement this result by showing that there is a dominant strategy mechanism that provides a 1 plus epsilon approximation for multi-unit auctions with decreasing marginal values. The communication complexity is logarithmic in m, n, and 1 over epsilon. So this is sort of like an FP task. So you cannot compute the optimal welfare efficiently, but you can get as close as you want. Okay. This is actually
Shahar, question. Do you know for classes that are smaller than decreasing marginal values, like special cases? Do you know if there is a gap between dominance?
Like what? What would be an interesting such class?
Matroid, the rank functions.
With multi-unit auctions? So matroid rank functions with gross substitutes valuations. Then there's still a gap. I think the proof works, or almost sure that the proof works. Shiri, do you know if the proof works for matroid functions?
I'm not sure, but I think that we can make it work. My guess is yes, but I need to check.
Yeah, okay. So we can probably make it work in the combinatorial auctions case. I mean, the proof is not very specific to gross substitutes, so I think it should be extended to most domains that you care about, if they have like certain properties. Okay, so this is the first set of results. Later, if we'll have time, we'll also discuss like some structural result about dominant strategy implementations, some new result on simultaneous algorithm, and an inapproximability result for dominant strategy mechanisms for combinatorial options. Okay. Let's start with the efficient revelation principle. Okay. So again, what I want to do is basically take two-player ex post implementation in some domain and make it a dominant strategy without paying too much in the communication complexity. And for that, we're going to use the taxation principle. And the taxation principle basically tells us that every ex post mechanism can be thought as follows. So each player I is implicitly presented with some menu mi. This menu mi is simply a function that assigns a price for each possible alternative. So mix is the price of alternative x. This mi depends only on the valuations of the others. And what happens in a truthful mechanism, in an ex post mechanism, is that the selected alternative x simultaneously maximizes the profit of all players. And profit is simply value minus price in the menu. Okay? So each player is implicitly presented with a menu. Each of them selects an alternative that maximizes his own profit, and some of their own select the same alternative. Just to make things a little bit more concrete, and suppose we have a second price option with values V1 and V2. V1 is the value of bidder 1, and V2 is the value of bidder 2. The menu that is presented to player 2 is player 2 takes the item at price V1, and player 1 takes the item at price 0. And you know, player 2 will prefer the option player 1 takes the item if V2 is greater than V1, otherwise prefers player 1 to take the item. Okay, so that's a menu. We need the notion of a taxation complexity. So what is the taxation complexity of an ex post mechanism? It's simply the logarithm of the maximal number of menus that can be presented to a player. So we fix some player, then we go over all possible valuations of the other players and count the number of menus that they present to the player that we have fixed. We take the logarithm of that number because we want the number of bits that we need in order to point to a specific menu that is presented. And that's the taxation complexity of the mechanism. Okay. And the main theorem in the previous paper was that in rich enough environments, and rich enough here means the modular, XOS, subadditive, and general valuations, all these are rich enough. The taxation complexity is essentially the communication complexity. Okay. And the theorem that we're going to prove in the next slide is that if we have if A is an ex post two-player mechanism for combinatorial options, say with general valuation, then there is a dominant strategy implementation of A, where the communication complexity is 2 times the taxation complexity plus the communication complexity of A. Okay? Since the taxation complexity is essentially the communication complexity, we see that we need only to triple the communication cost in order to get a dominant strategy implementation. Okay, questions?
Sorry, Shahar, I'm sorry,
Yeah.
I'm slow. I'm trying to understand. One menu is one function mi.
Yeah.
Correct?
Yeah.
And you are looking what is the maximal possible mi's. Am I correct?
Maximum the number of mi's, yeah.
That may be presented
to a player. You just count how many menus a player can see.
Okay, but not the size of each menu. That doesn't matter.
Not the size of each menu, no. But just the number of possible menus that the player can see.
But the player has to choose from the menu, right? So he has to point out from the menu a choice. That's his communication complexity, no? Something I'm missing here.
In a given instance, you are presented only one menu. But now I'll do the following thing. I'm fixing one player, and I'm just, you know, suppose we have only 2 players. And then I'm going over all possible valuations of the other player. For each valuation, you know, the player is presenting some menu to the player that we fixed. So Alice is presenting one menu to Bob. And then we go over all valuations of Alice and count the different menus that she presents to Bob. Okay?
Okay, but so you can ignore, what you're saying is that you can ignore the answer of Alice, which is which element of the menu she chose. That also should be counted in the communication complexity.
I mean, in the taxation complexity, I'm not counting this. I'm only counting the number of possible menus that she can.
Now, why not? Is it smaller? Is it significantly smaller always? Can you show that? Or is there any other reason that you don't count it?
It's almost the same, right? I mean,
I don't know. I mean, the menu, I mean, again, maybe in your environment that doesn't happen, but in principle, you could have 10 menus, each one is of size 1 billion, okay?
No, we're talking here about combinatorial options. We're talking here about
maybe in your environment doesn't happen, but then you have to claim that.
Okay, we're talking here about combinatorial options, like some other XOS, a relative or general valuations, and there we're fine. Yeah, then we don't get this floor. Okay. Okay, so let's see how to, like, in a sense, efficiently implement the revelation principle. See that we don't have to send too much information in order to get an explicit implementation. So we're going to have several rounds. The first one is going to be a commitment round, in which the players simultaneously exchange menus. Okay, so Alice looks at her valuation. She knows that, with this valuation, I'm going to present some valuation to Bob. I need, by definition, the number of bits that I need to represent this menu is just, to point to the index that represent this menu is tax 8 bits. So I do that, Bob doing the same. So this stage takes 2 times the taxation complexity. Okay, we call the taxation complexity is the logarithmic of the number of possible menus that each of the player can present to the other. So, just to point to one menu, we need tax 8 bits. Okay, so that's going to be the first step. Now the 2 players know that the menus that the other player presents to them. That's almost what we need, because ideally we can just ask each of them to compute his maximum profit bundle, and then just we're done. But that doesn't quite work because of 2 reasons. One, they might play like some strange way, like maybe Alice's most profitable bundle consists of items A and B. Bob's most profitable bundles consist of C, but he tells us that his most profitable bundle is B and C, and then we cannot just, we cannot allocate item B twice, and we don't get what the answer is. We don't get the valid allocation of the mechanism. So that's one reason why just if we ask this player just to tell us what his maximum profit bundle is, that doesn't work. The other reason is that we have like tie-breaking issues. Maybe I have several most profitable bundles and several most profitable bundles, and deciding which one I take depends on the other bidder. Then we still have to exchange some information. So what would be the trick to overcome this problem? We're simply going to run the algorithm. Again, that's going to take, by definition, the communication complexity of the mechanism. And then, if everyone plays as we expected, we get the right answer, and we didn't pay too much in the communication complexity. But it might be the case that player might play inconsistently. What does it mean to play inconsistently? There is no type, there is no valuation of the player, such that this player sends the menu that was sent in the first round, consistent with what was going on until now. Like maybe if I send the menu M1, then I must always send my first bit might always be 1. Okay, so if I send the menu M1 in the first step, and then when I run the mechanism, I send the first bit is 0, then I don't have a consistent play. In this case, we're just going to punish the player and say that he's not going to get any items at all. So he gets the empty bundle, and the other player can choose the bundle that maximizes his profit. Okay. If both players play consistently, then we're done. The outcome is identical. So note that we get a dominant strategy mechanism, and that might also answer the question whether whether only simultaneous mechanisms are dominant strategy ones, because here we don't get a simultaneous mechanism, but we get a dominant strategy mechanism because either you play consistently according to a type, and in that case, the ex post guarantee of the original mechanism guarantees that you get whatever maximizes your profit, or you play inconsistently. In that case, you're not going to get anything.
Shahar, so how do you handle this issue of ties if there are multiple maximizing bundles?
I simply run the original mechanism. I watch I observe what the original mechanism is doing, and I look at exactly in the same way.
So I think the original mechanism should have resolved them, so it will be resolved identically.
Yeah, tie breaking is defined by the original mechanism. So just I'm just observing what the original mechanism is doing.
Okay, thanks.
Okay. Okay, so that was for 2 players, and one new result that we have is that for 3 players, this doesn't work in the sense that there is an x plus function which has an x plus, which has an x. Sorry, there is a function which can be x plus implemented with polynomially many bits, but every dominant logic implementation requires exponentially many bits. Okay, so this trick is actually limited to only 2 players. We can't do that for more than 2 players. Okay. Okay. Let me actually skip the proof of the dominant strategy implementation of multi-unit auctions, and let's just go on to the second set of results. So the second set of results says that the communication complexity of every deterministic dominant strategy mechanism for combinatorial auctions with general valuations that achieves m to the 1 minus epsilon approximation is exponential. Okay, so now we're talking about approximation algorithm, and we rule out approximation algorithm, not just like exact welfare maximization. This theorem has 2 corollaries. One is that polynomial communication algorithms, not necessarily incentive compatible ones, provide better approximations than polynomial time communication complexity dominant strategy mechanisms. Okay, why is it so? Because we know that there are square root m approximation algorithms that require polynomial communication. So if you insist on dominant strategy implementation, the theorem tells us that the approximation ratio gets much worse. So that's a separation between what dominant strategy mechanism can do and polynomial communication algorithms. Note that in the ex post world, only recently a tiny separation was achieved. For 2 players with XOS valuations, we know that we cannot do better than 4/3 plus 1/108 approximation, whereas you can do 4/3 with polynomial communication. Okay, so and that required quite a lot of work. Was use the taxation framework. Here we get this much easily. And we also get that randomization actually helps because there are randomized dominant strategy mechanisms with an approximation ratio of square root of m. Okay, and again, if we insist on deterministic dominant strategy mechanisms, then the approximation ratio gets much worse. So that's also a separation between randomized deterministic mechanisms. We don't know such a separation in the ex post world. How do we prove this result? I'm just going to give you like a brief outline. So, as was already mentioned, there is a tight connection between simultaneous algorithms and dominant strategy mechanisms. Like, or let's put it another way, like many dominant strategy mechanisms are simultaneous. So it seems that the right thing to do is to try to bound the communication complexity of simultaneous mechanisms. Simultaneous algorithms are some framework that we introduced with in a paper with Noam and Sigal. The idea is basically that every player sends some polynomial message that is based only on his own valuation. They do it simultaneously. Then the central authority looks at these messages and based on these messages only computes the outcome. We proved that if the valuations are general, then you can't get anything better than m to the 1 minus epsilon. This is purely logarithmic theorem. It has nothing to do with incentive compatibility. So that's the first step. That's still not true because there are mechanisms, as we said, for general valuations that are not dominant strategies. But we are able to characterize all dominant strategy mechanisms for general valuations and prove that there are something that we call semi-simultaneous. Okay, so they're not simultaneous, but semi-simultaneous. And then in the third step, we sort of have to bridge the gap between the two. And we show that the communication complexity of every semi-simultaneous mechanism that provides an approximation ratio better than m to the 1 minus epsilon is exponential. And this is this gives us the theorem that we want. Okay, so that's the idea. I won't show you the simultaneous lower bound proof. Let's just let's actually see a non-simultaneous dominant strategy mechanism because I got many questions about before. Let's see a non-simultaneous dominant strategy mechanism. And it goes like this. We're going to consider only the domain of additive valuations. Okay. By additive valuations, it means that every item has a value, and the sum of a bundle is simply the sum of the values of the items in it. So that's additive valuation. And I'm going to show you that there is a mechanism that is really not simultaneous and is dominant strategy in this domain. So the mechanism works as follows. So Alice never going to get any item. So anything that she's doing is dominant strategy. So we're not going to worry about the dominant strategy of Alice. We're just going to analyze the dominant strategy of Bob. And the mechanism works by Bob first sending the identity of a single item J, and we ask Alice to send back the value, her value for the item J. Okay. And then Bob has to take a profit maximizing bundle among the following set. The price of every bundle S, as long as it is different, the size of S is different than 1, is going to be S. That is, we price 2 items at 2, 3 items at 3, 4 items at 4, 0 items at 0, and so on, except for bundles of size 1, in which we allow Bob to take only one particular bundle. This is the bundle that was sent in the first round. Okay, and we price that bundle at 1 if the value of Vij, if what Alice sent back is 1. Okay, if Alice value for the item is not 1, we price it at 1.1. Okay, so Bob sends a single item J. Bob sends a single item J. We can either take that item J at a price which is either 1 or 1.1 according to some function of the valuation of Alice, or we can take any bundle that is not of size 1 at the price of 1 for every item that he is taking. Okay. Questions? Yes.
Can you explain it again? The dominant strategy of Bob.
Okay. I'll prove that it's dominant strategy, but that's just is the mechanism clear? I need to prove that the dominant strategy I want to prove that Bob has a dominant strategy, but is the mechanism clear? No.
Yes.
Yes. Yes. Okay. Good. Okay. So now I want to prove that the dominant strategy of Bob is to send his most valuable single item. Okay. I want to prove that the dominant strategy of Bob is to send in the first round is a most valuable item, is item that has the highest value as a singleton. Okay? And let's see why it is the case. If Bob's most valuable item has a value below 1, then it doesn't really matter which item he is going to send. Like he doesn't want to take any single item because the price of every single item is above 1. Okay, so you know it doesn't matter which item he sends. He's still not going to take any single item, simply because the price is higher than his value. If his value is below 1. Okay.
But isn't it the case that in this case, he doesn't want to take any bundle at all?
In that case, he won't. Yeah, he will prefer the empty bundle.
Okay.
Okay. If there is only one single item with value above 1, then you know it's clear you're going to send that item. Maybe you want to take it, depending on what Alice is saying. Okay. But you know, there's no point in sending any other item, like any other item that is not J, because it's not profitable if there is only one item above 1. Now, what happens if Bob has 2 items with value above 1? In that case, suppose that these items are J and K. In that case, Bob might, you know, think, do I want to send item J or do I want to send item K? Okay. Maybe one of them has a price of 1, the other one has a price of 1.1. That might change my decision. But the point is that if Bob has 2 items with value above 1, then the bundle that consists of both of them together is more profitable than every single item alone, right? So in that case, it doesn't matter which item he sends, because he's never going to take, in that case, he's never going to take any single item. He's going to take a bundle that consists of at least 2 items. Okay, is that clear?
It's only weekly, right? There might be ties.
There might be ties, but it's still like the dominant strategy is to, you know, to send your most valuable single item. And note that this mechanism is really not a simultaneous mechanism. Bob sends some item first, and only then Alice gets back to him with the answer.
But it's a bit cheating because Alice is completely excluded. I mean, I could describe you another mechanism which is not simultaneous, where Alice is completely excluded, and then I just add some fake iterations just to make it sequential or not simultaneous. So what's
what? No, I don't understand.
So I might be missing something, but okay, here is a question. Does there exist a non-simultaneous dominant strategy mechanism for 2 players in which one of the players is not excluded?
I'm pretty sure you could change this mechanism to make sure that Alice gets something back. Like
always run this on half of the items and give Alice the other.
That's a little bit problematic, maybe running it on half the items, because like the answer in the first step might influence something else. But I'm quite sure that we can somehow change it in order to make sure that both players are doing something non-trivial.
Okay.
Okay. Okay. So we have this. Okay. This actually heavily dependent on the fact that the valuations were additive. If it doesn't work if the valuations are more general, like they have general valuations. If we have a general valuation, then this kind of mechanism is excluded. We know that the mechanism must be semi-simultaneous. So let me just give you the definition of a semi-simultaneous mechanism. So we'll need another definition first. So let's look at the game theory. Let's suppose that Alice plays first. Bundle S is decisive at price P for Alice. If there is a strategy of Alice that guarantees this bundle S, at price P regardless of the other strategies. Okay. For example, here in this tree, S is decisive because Alice can go left in the first round, and then no matter what Bob is doing, she's going to get S. Okay. And S prime is not decisive because Alice has to go right in order to get S prime. And if Bob goes left, then she won't get S prime. Okay? So a bundle is decisive if you can take it at price P, no matter what the other players are doing. So again, here Alice can make sure that she gets S, and but can't make sure that she gets S prime if she wants. Okay, so that's a bundle that is decisive. And now we say that the mechanism is semi-simultaneous. If, let's say for Alice, if the first time that she sends a message at the first node, at most one tree has leaves that contain decisive bundles. So here you can see that the leftmost tree, the leftmost tree contains bundles that are not decisive. You can't get S4. You can't guarantee that you get S4. If you go left, Bob might go right, and Alice might get S1. But everything that is in the right contains only decisive bundles. So the theorem says that actually, if you have a mechanism for general valuations, everything looks like that. You have one special message, which contains bundles that are not decisive, and everything else contains only decisive bundles. And one example, which maybe I should have given earlier and would have saved me for answering lots of questions, that an standing auction is actually also an example for a non-simultaneous mechanism that is a dominant strategy. Okay? And to answer your question, Michal, from before, this is an example where both players can, can take the items, and it's not a simultaneous mechanism. So why is it an example for a semi-simultaneous mechanism? Because we can think about like wait, be in the auction as the special message. If you quit, then you're decisive on the bundle that you get the bundle, the empty bundle at price 0. Okay, so that's an example for a semi-simultaneous mechanism. Okay. So what we prove is that all mechanisms for general valuations have this special format. We call it like a semi-simultaneous because it's almost simultaneous. I mean, if you don't send your special message, you know exactly what bundle you're going to take, because you're going to take some bundle that is decisive for you. So it means that unless you send a special message, you know what bundle you're going to take, and that's almost like in a simultaneous mechanism. You need to work quite a bit in order to get rid of this special messaging issue and get a general value bound. But that's the intuition. Okay. So let me just quickly summarize this. How we get this inapproximability result. We start with an algorithmic theorem which says that the communication complexity of every simultaneous algorithm that provides an approximation ratio better than M for combinatorial auctions with general valuation is exponential. We then have like a game theoretic characterization theorem that says that all mechanisms for combinatorial auctions for a region of domains are semi-simultaneous. And then we combine the two together and get the communication complexity of every dominant strategy mechanism for combinatorial auctions with general valuations is exponential. Okay? So that's how we prove this inapproximability result.
So Shahar, the second claim is about all dominant strategy mechanisms.
All dominant strategy mechanisms, yes. Yes. Okay, let me quickly summarize what we have with some open questions. So we prove for exact welfare maximization, we prove like that you need an exponential blow up in the communication for multi-unit auctions and for gross substitute evaluation. For multi-unit auctions, we know that to get the 1 plus epsilon approximation, you know, you don't need an exponential blow up. You can do it with not much communication. For gross substitute evaluations, the best dominant strategy mechanisms we know, deterministic dominant strategy mechanisms we know, achieves a poor approximation ratio of square root of m. So the obvious question is whether we can do anything better than square root of m with dominant strategy mechanisms. So obviously we don't know to answer that, but we are able to like do the first step in our inapproximability result, and we can show that we can lower bound the communication complexity of simultaneous non-inserted compatible algorithms, and show that it's no better than m to the 1/16. And now this in particular answers an open question from the paper with Noam and Sigal, and several follow-ups of it. Up until now, in the area of simultaneous algorithms, we could only bound the communication complexity, simultaneous communication complexity of X to S valuations. And we didn't even know if there is a 1 plus epsilon approximation for combinatorial options with some modular evaluations. And here we know that we can't get anything better than m to the 1/16 for gross substitute evaluations, and in fact also for metric-length functions. We also don't know how to get impossibilities for randomized mechanisms. There are several recent randomized mechanisms with very good guarantees, especially for subadditive evaluations and below. And we don't know how to bound the communication complexity of these. That would also be an interesting question for future research. Thanks.